Let's start with something familiar. Consider a prime of the form 2 to the h plus 1. In 1640, Pierre de Fermat proved that all primes of this form, other than 2, must have h as a power of 2. One proof of this fact goes like this. Suppose that h can be factored as r times w, where w is odd. Doing some modular arithmetic, we can find a divisor of 2 to the r w plus 1. In fact, we show that 2 to the r plus 1 divides 2 to the rw plus 1. But since 2 to the rw plus 1 is just 2 to the h plus 1, which is prime, the only way that 2 to the r plus 1 divides it is if the two are equal. This means that w equals 1. What we've just shown is that if w is an odd factor of h, then w is 1. Or in other words, the only odd factor of h is 1. And the only numbers with this property are powers of 2, so h must be a power of 2. Even if you've seen that before, I'll bet the following generalization is new to you. If b is at least 2, and there is a prime of the form b to the hm plus b to the h quantity m minus 1 plus b to the h quantity m minus 2 and so on, then m plus 1 must also be prime, and h must be a power of m plus 1. Now, while there's a lot to unpack here, we can actually rephrase our statement in terms of the base b integers. Notice that the earlier Fermat primes are just the primes that look like this in base 2. There are two 1s separated by a bunch of zeros. When written in base b, our generalized primes have n plus 1 1s, which are also evenly spaced apart by a bunch of zeros. Notice that the Fermat primes are just the special case of our primes, where b equals 2 and m equals 1. Looking at it like this, it becomes clear why m plus 1 has to be prime. Because if m plus 1 were composite, then there would be a composite number of 1s in the base b representation of p. Then, we could split up the string of 1s and zeros into a bunch of copies of the same number, finding one of its factors in the process. Since we know m plus 1 has to be prime, the new version of our statement looks like this. If b is at least 2, q is prime, and there is a prime of the form b to the h times quantity q minus 1 plus b to the h times quantity q minus 2 plus b to the h times quantity q minus 3 and so on, then h is a power of q. We've gotten pretty far with just the standard tools of number theory, but proving this last version of our statement inspires the use of something else entirely. In fact, we can proceed with a set of tools from complex analysis, known as the cyclotomic polynomials.
So what are the cyclotomic polynomials really? Well, there are actually a couple of different equivalent definitions, so I'll start with the one that's the most natural and use it to explain the more technical definition. A good way of arriving at the cyclotomics is to just factor the polynomials x to the n minus 1 into integer polynomials. You'll notice that as you increase n by 1, each time you'll see exactly one new factor that you haven't seen before. These new factors are the cyclotomic polynomials. Another way of generating the cyclotomic polynomials starts with factoring the polynomials x to the n minus 1 into the linear term, using the nth roots of unity. We can do the same thing that we did for the other definition, looking through the factorizations for things we've seen before and identifying what's left as a cyclotomic polynomial. As we do this, a pattern emerges. It seems that each of these cyclotomic polynomials factors into linear terms of the form x minus e to the 2 pi I k over n. And what's more, it seems that each of these fractions k over n is fully reduced, even when n is composite. This pattern still holds for the cases where n equals 1 and n equals 2, since 1 is equal to e to the 2 pi I 0 over 1, and negative 1 is e to the 2 pi I 1 over 2. If you think about it, this pattern makes sense. Any fraction k over n that can be represented using a lower denominator than n will appear before you get to the nth row. In general, the nth cyclotomic polynomial, denoted phi sub n of x, is equal to the product of all the terms x minus e to the 2 pi I k over n, where k ranges from 0 to n minus 1, and the fraction k over n is in lowest terms. K over n being in lowest terms is the same as k and n being relatively prime, so we'll rewrite that second condition for convenience. A simple corollary of this is that the roots of the nth cyclotomic polynomial are the complex numbers e to the 2 pi I k over n, where k and n are relatively prime. Keep these facts in mind for the rest of the video. Looking at the nth cyclotomic polynomials for prime values of n will give some insight as to why they may be useful for our problem. You may notice that phi sub 2 of x, phi sub 3 of x, phi sub 5 of x, and phi sub 7 of x all have this descending power structure, and so you could conjecture that for prime q, phi sub q of x is just x to the q minus 1 plus x to the q minus 2 plus x to the q minus 3, and so on. In fact, you would be correct, and you could begin proving this by rewriting the right-hand side using the geometric series formula. We can rewrite the left-hand side using our definition from earlier, and observe that k being relatively prime to q is the same as q not dividing k. If q is at least 0 and less than q, then the only way that q can divide k is if k equals 0, so our set of conditions just becomes 1 is less than or equal to k is less than q. On the right-hand side, we can factor x to the q minus 1 using the qth roots of unity. Observing that the denominator is just x minus e to the 2 pi I 0 over q, and cancelling terms, we end up with the same thing on both sides of the equation. We can use our newfound identity to rewrite our central claim once more. What we now want to prove is that if b is at least 2, q is prime, and there's a prime of the form phi sub q of b to the h, then h must be a power of q.
If I gave you a random integer and asked you whether or not it was prime, one of the first things you do is try to find a number that divides into it. Even though we're working with polynomials here, we can still do something similar. In fact, given the polynomial phi sub q of x to the h, you can always find another polynomial that divides into it, namely phi sub hq of x. Recall the definition of phi sub hq of x from earlier. Since phi sub hq of x factors into a bunch of linear terms, showing that phi sub hq of x divides phi sub q of x to the h is the same as showing that each of these linear terms divides phi sub q of x to the h. But this is the same as each of the roots corresponding to these linear terms also being a root of phi sub q of x to the h. More formally, what we need to prove is that for all k ranging from 0 to hq minus 1, where k is relatively prime to hq, phi sub q of x to the h evaluated at e to the 2 pi I k over hq is 0. Rewriting things, we get phi sub q of e to the 2 pi I k over q equals 0. But if k is relatively prime to hq, then k is also relatively prime to q. In other words, k over q is fully reduced, and e to the 2 pi I k over q is a root of phi sub q. Thus, we have that phi sub hq of x divides phi sub q of x to the h. In other words, there is some complex polynomial q of x such that q of x times phi sub hq of x equals phi sub q of x to the h. Note that since phi sub q of x to the h is a product of some terms, x minus e to the 2 pi I k over hq, q of x must also be of this form, and that this product may be empty. By our earlier definitions, every cyclotomic polynomial is an integer polynomial. Since we are multiplying q of x by an integer polynomial and getting back an integer polynomial, q of x must also be an integer polynomial. If we substitute b for x in our equation, since all of these are integer polynomials, q of b, phi sub hq of b, and phi sub q of b to the h are all integers. Since we're supposing that phi sub q of b to the h is prime, the absolute value of either q of b or phi sub hq of b must be 1. The absolute value of each of these polynomials is equal to the product of the complex magnitudes of a corresponding set of terms. Seeing the magnitude of b minus e to the 2 pi I k over hq in both of these products inspires us to study it in a bit more detail. The magnitude of b minus e to the 2 pi I k over hq can be interpreted as a distance between a point on the x-axis and a point on the unit circle in the complex plane. Notice that a straight line of length b is the shortest path from origin to b, so the length of this pink path is at least b. Varying our central angle theta, we see that the only way for the length of the pink path to be the same as the length of the green path is for theta to be 0. But theta is 2 pi k over hq, and since k is between 1 and hq minus 1, this is definitely not 0. That means that our inequality is strict. After shuffling some of the terms around and recalling that b is greater or equal to 2, we see that the magnitude of b minus e to the 2 pi I k over hq is greater than 1. This means that the absolute value of phi sub hq of x is greater than 1. And so the only possibility is that the absolute value of q of b is 1. Since each of the terms in this product is greater than 1, the only way for it to be exactly 1 is if there are no terms at all, and q of x is an empty product. This means that q of x equals 1 for all input values, not just b. In other words, if phi sub q of b to the h is prime, not only does phi sub hq of x divide phi sub q of x to the h, these two polynomials are actually equal. If these two polynomials are equal, then they must have the same roots. We know what the roots of phi sub hq of x are from earlier, and we can derive the roots of phi sub q of x to the h pretty quickly. Since e to the 2 pi I k over hq depends entirely on k, we can just focus on the k's. We'll finish things off here with a proof by contradiction. Suppose there is a prime r other than q which divided h. Then r would be an element of the set on the right, but it wouldn't be an element of the set on the left. This would contradict the fact that the two sets are equal, and so our supposition must be incorrect. In other words, the only prime factor of h is q, which is just the same as saying h is a power of q.
Now what we've done so far is all nice, but the keen among you may have noticed that we can prove something stronger with basically the same argument. Simply substituting an arbitrary integer a for q in all of the arguments we've made in section 3 won't break anything, taking us to a similar conclusion that if phi sub a of b to the h is prime, then phi sub ah of x is equal to phi sub a of x to the h. We can continue the argument from here in a similar way as before, so I'll just let the animation play. We end up with a much stronger result that, if b is at least 2, and there is a prime of the form phi sub a of b to the h, then all prime divisors of h are divisors of a. So aside from our central results, by understanding the essence of our central arguments, we've gotten all of these other results, essentially for free.